Welcome to Grade 11 Artificial Intelligence. In this module, we study reinforcement learning, how an agent can learn good behavior purely from the rewards it receives by trying things out. We'll build up the ideas step by step, then bring in deep neural networks to handle the hardest problems and meet some of the field's most famous results. Here is our plan for the lesson. We'll begin with learning by doing the agent environment loop. Then we'll define a Markov decision process and learn how Q-learning estimates the value of actions. We'll add neural networks to build deep Q networks and meet policy gradient methods. We'll see why an agent must balance exploration against exploitation and finish with the famous results and the hard challenges that remain. Reinforcement learning is learning by doing. An agent interacts with an environment step by step. At each step, the agent observes the current state and chooses an action according to its policy. The environment responds. It returns a new state and a single number called the reward, which says how good that step was. There is no teacher giving the right answer. The agent learns only from the rewards it collects by trying actions and seeing what happens. Its goal is not the largest reward right now. It is to maximize the return, the total reward gathered over the long run. To reason about this precisely, we need a model of the world, the Markov decision process. A Markov decision process, or MDP, is the formal model of an agent's world. It has 4 pieces. States describe the situations the agent can be in. Actions are the choices it can make. Rewards are the numbers it receives for those choices. And transitions say how an action moves the agent from one state to the next. Here, taking the action, go from state 1 earns a small reward, and reaching the goal state earns a large one. The word Markov names a key assumption. The future depends only on the current state and action, not on the whole history of how the agent got there. This assumption is what makes the problem tractable, and it underlies everything that follows. How does an agent learn which actions are good? We use value functions. The value of a state is the expected long-run return from that state onward. The Q value goes one step finer. It is the value of taking a particular action in a particular state. Q-learning estimates these Q values from experience. The agent starts with rough guesses. After each step, it nudges the Q value toward the reward it just received, plus the value of the best action available next. Over many steps, these estimates settle toward the truth. Then the agent simply acts greedily, choosing the action with the highest Q value, and a strong policy emerges. But there is a catch when the world gets large. Plain Q learning stores a Q value for every state and action in a table. In a real game with millions of possible screens, that table is far too large. A deep Q network fixes this. Instead of a table, a neural network estimates the Q values, so it can handle huge state spaces, even raw screen pixels. This is how a famous system learned to play Atari games directly from the picture on screen. A second family takes a different route. Policy gradient methods learn the policy directly, raising the chance of actions that turned out better than expected. They handle smooth, continuous actions well, like steering or throttle. The popular actor-critic methods combine both ideas. An actor chooses and a critic judges. An agent faces a constant tension. Exploitation means taking the action that looks best so far. Exploration means trying something new to discover whether a different action might be better. Exploit too much and the agent gets stuck on a mediocre habit. Explore too much and it never settles. A simple, popular balance is epsilon greedy. Most of the time, take the best known action, but now and then act at random to keep learning. We can also guide learning with reward shaping, adding small extra rewards as hints toward the goal. But we must shape rewards carefully. If the reward is badly designed, the agent will hack it, finding a loophole that scores well while doing the wrong thing. Getting the reward right is one of the deepest challenges. Reinforcement learning has produced spectacular results. Agents learned to play Atari games from raw pixels. A program called AlphaGo beat the world's best human at Go, and similar methods now control robots and balance data center cooling. But the field is still hard. These methods are sample hungry. They need an enormous amount of experience to learn. So we often train in a simulator which is fast but may not match the real world exactly. When rewards are sparse, arriving only at the very end, it is hard to tell which earlier action deserves the credit. And safety is a real concern. An agent optimizing a reward can learn behavior we never intended. Powerful then, but to be used with care. These ideas already make real decisions. In Rwanda, reinforcement learning can route delivery drones that carry medical supplies to clinics, choosing efficient paths. On power grids, agents help balance electricity supply and demand from moment to moment. In the United Kingdom, agents schedule heating and cooling to cut energy use in large buildings. In the United States, the same ideas drive recommendations and control fleets of warehouse robots. And in agriculture, an irrigation agent can learn when to water, saving both water and effort. In each case, an agent learns a policy from the rewards its decisions earn. Before we recap, let's clear up the common misconceptions. First, the reward is only the signal that defines the goal. It is not the agent's plan and not its policy. Second, value is about the long run, while a reward is just one step, so do not confuse them. Third, a deep queue network replaces the lookup table with a neural network. The core idea of queue learning is unchanged. Fourth, pure exploitation can trap an agent on a mediocre habit because it never tries the better option. And finally, more reward is not always better. A badly shaped reward can be hacked, rewarding the wrong behavior. Hold these in mind and your understanding will stay sound. Let's gather the key ideas. Reinforcement learning is learning by doing from reward in a loop of states and actions. A Markov decision process has states, actions, rewards, and transitions. Q learning estimates the value of each action, the Q value, from experience. Deep Q networks use a neural network instead of a table for huge state spaces. An agent must balance exploration and exploitation, and we shape rewards with care. The results are powerful, but the methods are sample hungry and demand attention to safety. Now, let's check these ideas with 3 quick questions. Here is the first question. What does the Q value estimate? The Q value estimates the long-run value of taking a particular action in a particular state, and then continuing to act well afterward. It tells the agent how good that action is, not just the reward of the next single step. Question 2. Why use a deep Q network instead of a simple Q table for an Atari game? Because the state is the screen of pixels, and there are far too many possible screens to store in a table. A neural network estimates the Q values across that huge space, so the agent can learn directly from what it sees. Last question, and it ties the module together. An agent always takes its current best action and never improves. What is the problem, and one fix? The problem is too little exploration. By only exploiting, the agent never discovers a better action. One simple fix is epsilon greedy, where the agent acts at random a small fraction of the time, so it keeps exploring while mostly exploiting. Excellent work. You now understand reinforcement learning as learning by doing, and you can describe a Markov decision process. You can explain Q learning, deep Q networks, and policy gradients. And you know why exploration and careful reward design matter. With this, you've completed our advanced grade 11 artificial intelligence series. Be proud of how far you've come and keep practicing. I'll see you again soon.